Hello everyone, welcome to the lecture series of pattern classification. I am Kundan Kumar, and if you would like to have these lecture slides, you can refer to my GitHub page at this given link. So, in previous lectures, we were discussing principal component analysis for feature dimensionality reduction. We saw that for a given set of feature vectors in d-dimensional feature space, we were looking for d-dimensional subspace where the reconstruction error of xi in the subspace is minimized. We formulated our dimensionality reduction problem in terms of squared error criteria function j0 x0, and we minimized j0 x0 by selecting x0 equal to m, where m is the sample mean. So, as we know that the sample mean does not reveal any variability in the data. So, we defined one dimensional representation of data as x equal to m plus ae and computed the optimal value of a such that the square error criteria function j1 is minimized, and that value was ak equal to E transpose xk minus m. So, here E was the direction of eigenvector corresponding to highest eigenvalue of scatter matrix of set of samples in d-dimensional feature space. So, if you will look at this term, this is xk minus m, where m is the sample mean, which is given by 1 by n summation over k equal to 1 to n. So, this is the expression for sample mean. So, this term is basically the 0 centered feature vector, and when we multiply this 0 centered feature vector with the eigenvectors, basically we are transforming this 0 centered feature vector to a new domain or new feature space that is represented by the eigenvectors corresponding to highest eigenvalues of scatter matrix. So, we have also discussed the extension of one dimensional representation to d-dimensional representation of feature vector, and we defined the criteria function something like this. Okay. So, where E1, E2, ED dash are the basis for the subspace, because E1, E2, ED dash are the eigenvectors of first D dash highest eigenvalues of scatter matrix, where the eigenvectors are orthonormal. That means the magnitude of each eigenvector is unity and each pair of eigenvectors are basically the orthogonal, and ai is the projection of xi into that subspace. So, where that scatter matrix of set of feature vectors were defined by using this expression, which is related to the covariance of the feature vectors. Here coefficients are basically the projection of feature vector, which is also called the principal components. So, here one point can be noted down that when the eigenvectors are sorted in descending order of the corresponding eigenvalues, the greatest variance of the data lies in the first principal component and the second greatest variance on the second component, and so on. Now, let us try to solve this problem. We have given the following set of feature vectors belonging to two class omega 1 and omega 2, which are Gaussian distributed, that is assumed. Then find out the base direction of the line projection that best represent the data in one dimensional feature space. So, here we have to find out the direction of the line of projection that best represent the data in one dimensional feature space, something like this, in this direction. So, this is E1 and the other direction will be E2. So here question is asking about the best representation of data, not the separability of the data. So here we need to apply principal component analysis, and we can omit the class level information. So here we will consider feature vectors without class label. So let us try to solve this problem. So we will have the set of feature vector as so these are the feature vectors where x is basically have the two feature components x1 and x2 in two dimensional feature space. So here we have how many samples? So n equal to 10. So now just try to analyze the data and plot in two dimensional feature space. So these are the data points which is plotted in two dimensional feature space. So we can observe from this scatter plot that direction of maximum variance is in this direction, and this is basically the first eigenvector corresponding to the largest eigenvalues. So that need to find, and so that this eigenvector we will find using the principal component analysis. So as we discussed that the E1 is the eigenvector corresponding to the largest eigenvalue of the scatter matrix. So as we know that S is our scatter matrix, which is given by xk minus m into xk minus m transpose. So we have to compute this term. Before computing scatter matrix, we need to compute the sample mean m equal to 1 by 10, because we have the 10 samples, k equal to 1 to 10 xk. Okay. So here xk is basically the two dimensional feature vector. So m will be also the two dimensional vector. So when you will compute it, so how we can compute? We have to add all the first feature and we have to take the mean value. That means 1 plus 3 plus 4 plus 5 plus 7 plus 6 plus 9 plus 7 plus 11 plus 13 divided by 10. So when you will compute, it will be 6.6. So similarly, we can compute the second component of the mean feature vector. It will be 3.8. So now we can compute the scatter matrix. So now let us compute the scatter matrix. So S equal to so it will be 10 samples. So k equal to 1 to 10 xk minus m transpose. So it will be 1 minus 6.6, 2 minus 3.8, 1 minus 6.6, because this term is the transpose of this term. plus, so I am writing the subtracted values directly. So then we obtain this term. So you can solve this term. So when you will add all individual terms, we will obtain 120.4, 26.2, 26.2, 6. So this is our scatter matrix, and this is real and symmetric. So when we compute the eigenvalues and eigenvectors of this scatter matrix, then we will have the orthogonal eigenvectors. Now let us solve this scatter matrix for the eigenvalues and eigenvectors. So to compute the eigenvalues and eigenvectors, we need to write the characteristic equation. So characteristics equation can be written as S minus lambda I, the determinant equal to 0. So we can put here S is basically the 120.4, 26.2, 26.2 minus lambda 0, 0, lambda, and we have to take the determinant of this term and we have to equate to the 0. So now we can write as 120.4 minus lambda 26.2, 26.2, 15.6 minus lambda, and we have to take the determinant. Now we can compute the value as, so we can write 120.4 minus lambda into 15.6 minus lambda minus 26.2 square equal to 0. So now we can solve it. So it will be 120.4 into 15.6 minus plus lambda square minus 26.2 square equal to 0. So now we can rearrange and we calculate the values. So finally we have the quadratic equation as lambda square minus 136 lambda plus 1191.8 equal to 0. So we can solve this quadratic equation. So when you will solve this quadratic equation, you will find the two eigenvalues as lambda 1 equal to 5. So lambda 1 equal to 126.58 and the other eigenvalue 9.415. Now we can find the corresponding eigenvector. We know that S E1 equal to lambda 1 E1. So to compute the eigenvector E1 corresponding to the eigenvalue lambda 1, it must satisfy this equation. So let us consider that E1 is basically the E11, E12. So, it has a 2 component and E2 equal to E21 and E22. Okay. So, these 2 eigenvectors we need to calculate. So, let us take this eigenvector. So, we will have 120.4, 26.2, 15.6, and then we will multiply E11, E12 equal to, so lambda 1 is 20. So, lambda here lambda 1 is 126.58 and then E11, E12, then we can solve it. It will be 120.4 E11 plus 126.2 E12, 26.2 E11 plus 15.6 E12, and you have to, and we have to equate this with 126.58 E11, 126.58 E12. Okay. Now, put E11 equal to 1 and compute E12. So, when we will do that, it will be 120.4 plus, so we are considering this first row, E12 equal to 126.58. So, when you will solve this, then E12 will be 0.23. That means E1 equal to E11, E12, and the values are basically 1, 0.23. So, here you can see that E is basically not a unit vector. So, we have to make it unit vector. So, how we can make it unit vector? Just we have to compute the magnitude of this vector and we will divide to each element. We will make the unit vector. So, how we can make the unit vector? 1 divided by the magnitude of this vector. Okay. So, when you will solve it, we will obtain 974.5 0.2241. Okay. So, this is the basically our E1. Similarly, when we will proceed for the E2, then we have to solve this expression. We have to solve as E2 equal to lambda 2 E2, and then we can compute the value of E2 in the same manner. So, E2 will be minus 0.22 0.97. So, when you will calculate, maybe these decimal places it may vary, but you will approximately you will obtain these two eigenvectors. So, this is the basically the direction of the first eigenvector corresponding to the highest eigenvalues. So, this is the direction where we can project our data so that we will get the maximum variation in the data. Okay. So, this is the solution. This is the solution of our given problem. Now, just we can analyze this problem as that how we can compute the principal components. What is principal components? So, basically A1 is 0. So, how we can compute the principal components, like A1 is the principal component of x1, A2 is the principal component of x2, and so on. So, An is basically the principal component of x. So, we can compute A1 equal to A transpose x1. Similarly, A2 equal to A transpose x1. The same way, An equal to A transpose xn. So, here A is basically the transformation matrix which is consist of the eigen vectors, or we can write E11, E12, E21, E22. So, here for this case, for the given problem, the transformation matrix is 0.97, 0.22, minus 0.22, 0.97. Okay. And if you would like to reconstruct the feature vector x1 from the transformed feature vector a1, then x1 will be a into a1. So, this is the basically the reverse. That means we can reconstruct our feature vector using this transformation function, but without the transpose. Now, let us take this example. So, here we can verify, we can take one feature vector and we can verify this relation. So, let us take x1 equal to 1, 2. So, a1 will be, so we have to take the transpose of a. So, 0.97, 0.22 minus 0.22, 0.97, and then we have to multiply 1, 2 equal to 1.41, 1.72. So, this is our the transformed feature vector corresponding to this, and this is in the transformed domain. Okay. Now, we want to compute x1 from a1. So, x1 equal to a1. So, we can multiply 0.97 minus 0.22, 0.22, 0.97 into 1.41, 1.72. Okay. So, just solve it, we will obtain 99. So, basically this is approximately 1 and 2. So, whatever the loss we are incurring here, just because of the different decimal places, but we can exactly reconstruct our feature vector using this transformation matrix. Okay. So, in the same way we can transform our two-dimensional feature vector on one-dimensional feature vector. So, how we can do that? In the same way, but here our transformation matrix will be only E1. So, for one dimensional transformation A1 equal to 0.97, 0.22 into 1, 2. Okay. So, we can compute this term, it will give you 1.41. So, again we can reconstruct x1 using this term, but this time we cannot reconstruct the exact value using only the one dimensional representation. So, whatever we will represent and whatever the reconstruction will be done, so that will be basically in the least square sense. So, let us see this iris data set representation. So, here the iris data set is basically very famous data set and used for the data analysis problems like classification, feature reduction and many more. So, this data set we can collect from the UCI machine learning repository at this given link, and this iris data set contains the measurement of 150 iris flower from the 3 different species, and these 3 species are basically the iris setosa, versicolor, virginia, and from each species that we can call it the class, we have the 50 number of samples. So, we have total 150 samples and from each class we have 50 samples. So, what are the features that is considered to prepare the iris data set? That is basically the sepal length, sepal width, petal length and petal width. So, from this image it will be very clear. So, this is basically the sepal and this is the basically sepal length, this is the width, this is the petal length and this is the petal width. Okay. So, in this way we have the iris data set of the dimension 150 samples and each sample having the 4-dimensional feature vector. So, iris data set having the dimensionality of 150 cross 4, and also the one dimension is given for the class label. So, we have the class labels as well. Okay. So, this is the scatter plot of the iris data set, which tells about that how the two feature vectors are related to each other. Like if you will consider the first block, so this is the basically the sepal length versus sepal length. That means we are talking about the first feature column and there we compute the histogram of the first column. This is the histogram of the second column, second feature vector. This is the histogram of the third feature vector and this is the histogram of fourth feature vector. So, if we try to find the scatter plot between the first feature and the second feature vector, then this is the basically the scatter plot between the first feature vector and the second feature vector. Basically here we are visualizing the feature in 2-dimensional feature space. So, if we consider first feature vector and the second feature vector, then this is the scatter plot of the first and second feature vector. Similarly, this is the basically the third feature vector and fourth feature vector. So, this is the third and fourth feature vector, the scatter plot of the third and fourth feature vector. So, in this way we can analyze that which feature having what relation with the other features. Okay. So this is just for visualization, that means how one feature vector is related with another feature vector. But we can use the PCA to reduce the dimensionality of the feature vector. So in iris dataset we have the 4-dimensional features, so we can reduce it to 2-dimension or 3-dimension so that we can visualize the feature vector. So we can apply here, this is the basically the iris dataset in 2-dimensional feature space after applying principal component analysis. So on the x-axis basically the first eigenvector, and on the second axis this is the second eigenvector. So this is the direction of the two principal directions. So how the feature vectors are separable. So basically the main idea of the PCA is that we are trying to uncorrelate the feature vector. Okay, and this is the 3-dimensional representation of the 4-dimensional feature vectors, and that we obtain using the PCA. Thank you for watching. If you have any doubt, please ask in the comment section. Thank you.